You now know enough to do assignment 1. There'll be a more refined description of how you're supposed to hand it in. I talked to a couple of random students and the TAs, and they'd rather hand it in on paper. So we'll get you to hand it on paper. So we'll tell you what the, we'll give further instructions. But we'll get you to hand in the code so we can test it. A few people asked about the midterm, and they'd rather it was confirmed than tentative, so it's going to be on the Monday, the 26th of October. No one's complained about that time, and so it's good to confirm it. And are there any questions about anything? Okay. So today's so the review of what we've done over the last couple of weeks, we've done search, and we're going to start something else today. So here's the review of what we've done. We've done a number of search techniques of where we change what the frontier is. Okay, the only difference between depth first, breadth first, lowest cost, best first at A star is how we're going to order the frontier. Then there are two techniques we used for reducing the search. One is to do loop detection, which removes a path, loops back onto itself, and the other is multiple path pruning that removes subsequent paths to nodes. Okay. We had this thing for A star, a restriction on H called the monotone restriction, that if the heuristic function follows that A star will find an optimal solution even with multiple path pruning. We looked at iterative deepening by recomputing elements of the frontier, and it saves space. Depth first, branch and bound was used for finding optimal solutions with linear space. And sometimes you could go forwards or backwards or do bidirectional search. Okay, are there any questions about any of those things? All right. So here's a quicker question. I thought this is the one that was up there earlier. So what's not true of depth first, branch and bound search? Right. A, it always finds an optimal solution if the bound starts as an overestimate of the cost of an optimal solution. B, the bound always reduces whenever a new best solution is found. C, it does not necessarily halt if the bound is infinite. D, it uses linear space even if used with multiple path pruning. And E, if it halts and returns a path, the path is an optimal solution even with loop detection. Only one of them is true. Only one is false. Sorry, only one of them is false. Only one of the answers is correct. Sorry. Does anyone need more time? All right. Where am I? The answer is D. All right, it doesn't use linear space. This is D. Actually, a sizable number of people answered all of them. If the bound starts as an overestimate greater than it, it always finds a solution, right? Because there's only a finite number of elements. Yes? Or no, an overestimate means it's a number that's an overestimate of the... If it's infinity, it doesn't always find a solution, but if it's just some number that's an overestimate. But if you're estimating the size of someone, you don't say infinity. You know, infinity is not an estimate. You say, what's the size of the tallest person then? And you've got to be correct. Then you don't say infinity. It's just... what we did there is the bound kept reducing, because we only reduced, remember how we found the bound? Right, remember we found a new best solution was because the path was better than the previous one, so we kept improving it. So this bound always keeps reducing all of what times through it. If the bound is infinite, it doesn't necessarily halt. So if you really believe that this, you'd answer, yes, it doesn't necessarily halt if the bound is infinite, because it just can go on to an infinite depth first search. If you use multiple path pruning, you have to remember everything, so it uses exponential space. So D is the correct answer. And if it halts and returns a path, then then it returns the optimal solution. So it's found at least one solution, and it's then going to keep iteratively improving it until there's no more solutions found. Okay, any questions about that? Okay. I like these because they give you, let me review what's happening in branch and bound. All right. Next one. What's true of depth first branch and bound? A, it uses as much space as A star. B, it always halts and finds an optimal solution. C, it can get confused if there are multiple optimal solutions. D, the first time best is assigned a value, it has found the best solution. Or E, none of the above. All right, how are we going here? Do you need more time? Anyone need more time? Need more time? Stop that. Ah, good. The answer is, in fact, E. It doesn't use as much space. Remember, it keeps doing depth first search. A star search uses exponential space. So the reason you use depth first branch and bound is because it uses less space. It doesn't always halt, which is what we even had a discussion about that. If the bound is infinite, it doesn't always halt. And if there are multiple optimal solutions, it just returns the first one. It doesn't get confused at all. It doesn't do anything. Yes?
How do you find an optimal solution in like a depth, a DFS or BFS, if there's like no cost or heuristics involved? Just a solution is an optimal solution?
Well, then you're trying to, often we just use a cost of 1 for an arc.
Okay.
So we just use a cost of 1, so then that's the shortest path. Yeah, so if you have a cost of 1, then you just have we're just counting the cost corresponds exactly to the length.
Okay.
Yeah. Any other questions? All right. One more. Oh. Let's go here. So which of the following is true? A star with multiple path pruning is always the best algorithm if you have a heuristic function. B, depth first branch and bound is always the best search algorithm because it uses linear space. C, lowest cost first search with multiple path pruning is always the best algorithm if you need to find the lowest cost solution and don't have a heuristic function. D, multiple path pruning always makes a search algorithm better. Or E, there is no search algorithm that's always the best. All right, anyone need more time? Yay, everyone got E. Good, there's no search algorithm that's always the best. Good. All right. How am I going for time here? All right. At the end of last time, I talked about dynamic programming. And I had a few questions about it, so I sort of changed the slide slightly because people were confused about cost. You can think of this as cost to goal. What we're building here is a cost from node n to a goal, and that's like an array. We're just going to save or store all of them. So we're going to find the cost of the least cost path from node n to a goal, and we can build it backwards from the goal. The cost to go of n, node n is 0 if n is a goal, otherwise it's the minimum of the costs from n to another node m plus the cost to the goal from m. Okay, this is almost a definition of what the cost is. And if we're going to, if we're at a node n, we can work out what to do, because we're just going to choose the m that minimizes this value. Okay, we're going to choose that m that minimizes this value. Okay. And what's interesting for us here is this is like which method on the inverse graph? What method's it like? We're going to search. So imagine having this inverse graph. Right, we're going to search backwards from the goal. Right, and we're always going to keep choosing this. We're always trying to find the cost to go of this node. So what's it like? Yeah. Yeah, so it's like least cost first search on this inverse graph. So what we're going to do is we're just going to have this priority queue, and we're just going to keep selecting the least cost path on this inverse graph. And that's actually, people often refer to it as dynamic programming, of trying to find a solution to a goal. Okay, so lots of these algorithms that we've, right, and we're going to keep, and if that's, right, we can just keep building this space to G, and now you know the algorithm, right? It's just given a goal, it's going to try and have a priority queue and keep choosing the smallest one of these and keep building it back. So once I tell you that it's this, you know the algorithm. There are two main problems with it. One, it requires the same problem as it requires this big table of this cost to go. And the second main problem is you need to recompute this for every goal. If we ever change the goal, we're going to recompute this. But you can also imagine including a heuristic. If you have a particular start node, you could also imagine doing a star search backwards, and then you're going to just essentially just go towards our particular goal. So now we can ask the question, should path finding on a map use forward or backward search? So if you're building Google Maps, what would you do? Right, so if we have a sort of a Google Maps thing, what would we do? Because if you're trying to find a path across some grid and things, you know, we try to find roads up to Stanley Park, and there's multiple routes, right? Stanley Park's here. And there are a whole lot of different routes we can take from UBC. What would you suggest and why? Yeah. You could do both, but in fact they don't. It's a good suggestion, but it turns out that they don't do this. There's a reason why they do one or the other. Well, we're effectively going to do a sort of like an A star search. So we're going to use A star because basically we've stored all of these nodes. There's not that many nodes in this graph, right? So the space is not a problem. But it turns out that the best thing to do is to go backwards from this goal, because people don't actually follow the route they're given. And if you keep finding for every node, we keep saying from here the best place to go is. So what happens is you end up with a graph that says for every node, it says go here. And for this node here, it might say go there. And for this node here, it might say go there. Right? So this graph here, when we build it up, effectively has for each point, it says which way to go, because that's what we're building up. Whoops. Right, so we're building up this big graph. For every point, it says which direction to take. And if someone takes the wrong direction, if someone moves from there, we've already computed what to do from that point. Right, so often they go effectively A star search from the inverse graph, and you keep all of these things so that if someone changes their mind and goes the wrong direction, you've already computed where they should go. Okay, we don't need to replan. Does that make sense? No. So you can just keep all these things so that when people accidentally turn left and they need an answer immediately, what should I do? I couldn't follow your directions. You can tell them, go right now. Okay, because you've already computed that. Okay, any questions? Okay, good. All right, so what we're going to do today is we're going to start on what are called constraint satisfaction problems. And so at the end of today, what we should be able to do is to recognize and represent constraint satisfaction problems, show how constraint satisfaction problems can be solved with generate and test, and then we're going to show how they can actually be solved with search. So the overview of the course we've done is we've looked at search, which was deterministic, fully observable. We can represent elements in the nodes in terms of states. We're allowing it to go indefinitely. We're going to look at goals, and we're going to look at perfect rationality. And what we're going to do now is really to go from states to extend it into features. So what we'd like to do is, instead of just having states which are unstructured, which are just this node or this node, we're actually going to try and exploit the fact that we can describe states in terms of features. And that's what we're going to do now. Okay. Right, so a CSP is characterized by, there's a set of variables, which we're going to assume they're just finite, there are just n of them. Each variable has a domain which specifies a set of values, possible values the variables can take. And here we're going to assume they're finite. And we're going to have a possible world, or sometimes we call it a total assignment, is an assignment of a value to each variable. Or sometimes it's just called worlds. So we're going to have this, so we have a whole lot of variables. We're going to give lots of examples. And then we're going to have these hard constraints, specifies which combinations of these values are legal. And a solution or a model is a possible world that satisfies all the constraints. So now we have all these constraints on things. So the typical example you do is map coloring. Right, so we want to assign a color, red, green, or blue, to each of the states here in Australia so that the neighboring states have different colors. Okay, so that's the problem we're going to look at here. So what are the variables? What are the variables? Yeah, right, so the variables are the states. Here are the states. And what are the values? So what are the domains? The domains is a set of values. What's the domain for each variable? Yeah, the domain is the color. Okay, so here it's just red, green, or blue. And so one solution is an assignment of a color to every state. So one solution to this is one solution. We're going to assign red to Western Australia and green to the Northern Territory and New South Wales, and red to Queensland, and blue to South Australia, and red to Victoria, and green to Tasmania. So this is a solution, right? It's an assignment of value to each variable. Okay. So how many possible worlds are there in this one? Well, how many assignments are there? How many assignments are there to Western Australia? So there's the Western Australia. It can either be red, green, or blue. And the Northern Territory is either red, green, or blue. And South Australia is either red, green, or blue. And Queensland, etc. So how many states are there? Total, so how many possible worlds are there? So possible world is an assignment of value to every variable. I'm asking how many solutions there are. I'm asking how many assignments of values to variables there are. Any other suggestions? So there's 3 for this, times 3 for this, times 3 for this, times 3 for this, and there are 7 variables. So there's 3 to the 7 possible worlds, right? Does that make sense? That's just how many different combinations there are. Okay. What was that one? And what are the constraints in this? So what are the constraints in here about the assignments of values to variables? They're all going to be different colors to their neighbors, right? So tell me one constraint that we're not allowed to have. Yeah. Right, so we can think of WA as a variable, and that's not equal to the NT, right? And we have Western Australia is not equal to South Australia, right? And Northern Territory is not equal to SA, right? And Northern Territory is not equal to Q. So for every of the borders in there, there's an inequality constraint. So these are the constraints. Okay, does that make sense? Any questions about that? So there are lots of different variants we can do. One is to determine whether or not a model exists, whether or not there is a solution to this assignment. So in this case here, there was a solution because we found one. We could actually find a model, find a particular assignment of the values to the variable that satisfies all these constraints. We could find all of the models. You could imagine asking how many models are there. You could count them. We could find the best model given some model quality. And they were often called soft constraints, which we'll look at later. So first of all, we're not going to do this. If we could find the best model, according to some model about when some is better than another, and then we have these soft constraints which specify the preferences, and we could determine whether some property holds in all of the models. So we could ask, is there something that must be true in all of the models of this? All right, so they're the variants that we can have in here. So let's look at a few more examples. So this is the example that we're going to do. There are 5 variables, A, B, C, D, and E, that represent the starting times of various activities. We have the domains of each of them they can either start at 1, 2, 3, or 4. So this is the sort of example that we might have, sort of abstract example we might have. So what are some possible worlds? So what are some possible worlds for this example? So what's a possible world? We could just assign a number to each variable, right? So a possible world might be A is 1, and B is 2, and C is 2, and D is 3, and how many variables are there? And E is 4. Right, there's a possible world. It's an assignment of value to every variable. Or, A is 1, B is 1, C is 1, D is 1, and E is 1, right? Does that make sense? Any questions? How many possible worlds are there in this? I can't hear. 4 to the 5. There are 4 to the 5th possible worlds. I never remember whether it's which way you put the power, but you just think about it. Well, there are 4 ways of this times 4 ways of this times 4 ways of this, and so it's 4 to the 5th, right? Don't try and remember an equation. Just think of how it works, right? There are 4 assignments of this, and you've got to multiply them by the 4 assignments to this, and multiply by the 4 assignments to this, and then you won't mix up which of those. Right? If you know the principle, why it works this way, we could do it. Okay, any questions about that? 4 to the 5th. And there are a whole lot of constraints here. And maybe B is not equal to 3, and C is not equal to 2, and A is different to B, and B can't be at the same time as C, and C has to be before D, but A has to be at the same time as D, and E has to be before A, and E has to be before B, and E has to come before C, and E has to come before D, and B can't equal D. And we end up with problems that you probably can't guess a solution to it. I don't know a solution to it. I know there is one. So it's sort of not, so these things, and given an arbitrary constraint, it's not that hard, it's not that easy to solve them. You can start guessing randomly, which we're going to try. That's one of the algorithms we'll do, is to guess randomly. What the other algorithms we'll give are just trying to rule out values, saying, well, E can't be 4 because E's got to be less than C, so you can start ruling things out. There are a whole lot of different algorithms we're going to do to look at these problems. Okay, questions? I'm not going to give you a solution because I don't know what it is. No? We will solve it. We'll solve it. All right, so here's another example. Here's a crossword puzzle. So here's a crossword puzzle for, a very tiny crossword puzzle. There are 4 words to put in. 1, 2, 3. Sorry, there are 5 words to put in. There's 1 across, 1 down, 3 across, 4 down. So what are the variables in here? So what might how would you represent this? Yeah.
The variables are 1, 2, 3, 4. So like 4 positions you can put a word in. Or 1 across, 1 down.
1 across.
2 down, 4 across, 3 across.
1 down. 3 across. 2 down. I can't read it. What's the other one? Okay, and how many values can this have? 1 across. So what's the domain of this? Right, has to be 3 letters. So it says 5 possibilities, right? So there's and, whatever it is, to, has. There are 5 possibilities. How many possibilities are there for 1 down? Are there 5? Oh, they're not all 5. Oh, they're all 5. Okay. 5. So they're all 5. So how many possible worlds are there? They're all 5. What are they? What are they then?
There's a 5-letter word, peace.
Hmm?
Peace is a 5-letter word.
There's only 4 6-letter words.
So what's the answer? So what should I change?
2 down has 4 options, not 5.
2 down has 4 options. Thank you.
And one of the options is unused.
Okay? So how many possible worlds are there? I didn't think they were all the 5s, but... How many possible worlds are there? Yes, so there's 5 times 5 times 5 times 4 times 5. So there's 5 to the 5th. Sorry. 5 to the 4th times 4.
Shouldn't 2 down be 5? There's 5 or...
I think beast is a 5-letter word. But I can't see you. I think there's only 4. So what are the constraints? So what are the constraints in here? Yeah. Right, so 1 across. So the first letter of 1 across equals the first letter of 1 down. What's another constraint? Well, okay. We could do that. Size of 3 across equals 4. Yeah. Yeah, we sort of assumed it was true, but that's fine. There's some of these constraints we'll put in that, like, these are actually called domain constraints that restrict the domains of them. What's another constraint? So the fifth letter of, what was it? 2 down has to equal the first letter of 4 across. Okay? There's a whole lot of them. Does that make sense? There's actually another representation for this of where the variables are each square and the domain of each of them is A to Z. But the size for that's actually much bigger than this, but it's actually another constraint, another possible one. So if we have a big crossword puzzle like they have in the newspapers, and let's suppose so people know about 50 to 100,000 words. So if you think about there are 10,000 words for each letter of each length, how many variables are there in this? Oh, I don't know how many variables. That's a good question. So there are about 100 variables, right? And each of them contain 10,000, so they're approximately right, so there are approximately 100 variables. And each one of them has 10,000 words, so how many possible worlds there are there? Is what? What is it? There are 100 variables. They each have a domain size of 10,000. How many possible worlds are there?
100 to the 10,000.
Right? Oh. Oh. Which one is it? The first variable, there are 10,000 choices. The second one. Yeah. No, there would be, but there are more squares than 100. This is the answer. That's wrong. So if you did, say there are 200 squares, I don't know how many squares there are. How many squares are there? So if there are, if the variables are the squares, right, and each can contain (26 letters). One of 26 letters, then there are approximately How many squares are there? Approximately 200 squares. Squares. How many possible worlds are there here? To the 26 to the 200 possible worlds, right? All of these are getting to be ridiculously big numbers. Want it the other way around? Does that make sense? All right, good. Who knows how Sudoku works? Who doesn't know how Sudoku works? Couple. So in here, we're going to solve a Sudoku problem. So on the next assignment, we'll actually get you to solve a Sudoku problem. So what are the variables in here? Right, so each Sudoku, so each square, so the variables are the empty squares and what are their domains? Right, let's set 1 to 9. And how many possible worlds are there? Or how many variables are there? So there are 9 to the 81 possible worlds. Is that right? We get to, yeah. Sorry? Well, for this one. So what's wrong with this?
Some of the squares are already set in place, so you should just be counting the empty squares.
We said they're empty squares.
Yeah, so it should be 9 to the however many empty squares there are.
Right, so it should be about 9 to the 60 or something.
Yeah.
As there are approximately 60 empty squares. So I think that's wrong. I think that's right. Does that make sense? You could have told me there's a variable for every square, and this would be the right answer. Right? Or you could tell me, but there's a variable for every each square, and then this is the answer. So depending on how we debate, the answer to this question depends on how we define a variable. Any questions about that? So what are the constraints about Sudoku? For those who don't know about Sudoku, what are the constraints? Someone tell me what the constraints are. What are the constraints? Yeah. Well, you can't have 2 in the same number in any row. You can't have 2 in the same number of any column, or 2 in the number in any of the squares, the top left square, or I think there are dark lines around the squares in here. So you can't have 2 the same in any square. Okay, and they're essentially the 3 constraints here. And so the constraint satisfaction problems people seem to find them fun to do, because there are these people publishing in the newspapers every day, so they're sort of challenging for people. But here's a real example that does it. UBC final exam schedules is actually carried out by an AI system. The person who wrote it, I'm actually going to come to class in about 2 weeks after we've done all this. He's going to tell us how it actually works. But here there are 13 exam days. There are 52 time slots. There are 30,000 students who take exams. There are 1,700 sections with exams. There are 105,000 student exam pairs, and there are 274 rooms across 38 buildings that can be assigned to rooms, right? So this is the sort of real-world example that we can start solving in these things. So what are the variables here? What variables are there? So what do we have to assign? So I could. We assign. Okay. Right. So think about it as. I think they use sections as this. Okay. So what is each? So tell me a variable that. So there's a variable for every. There's a variable for each course, for each section. And what's the domain of it? What's the domain of that variable? Well, we're not assigning a course to every student. What are we assigning to each course? A location. Domain is a location. And there's another variable for each. There's another second variable for each section, which has the domain what? The time, right? So in fact, 2 variables for each section. We have to assign a location and we have to assign a time. For every course, we need to assign a location and a time that's going to be in, right? Does that make sense? That's the game. That's all we have to do. Okay, the domains of that. How many possible worlds are there, approximately? So how many, if we want to assign a variable to every section, how many of this are there? So we want to assign a location to every section.
274 to the power of 1,700.
Sorry, say that again. I can't see it.
274
Times.
to the power of 1,700.
Right, and what's the other one?
274. Oh yeah, fine.
So I can't read it. My neck doesn't work that way. Tell me.
52. Is it the time slot? To the power of 1,700 again.
Does that make sense? It's a big number. There are lots of possible assignments of courses to. There are lots of possible assignments to courses to rooms and to times. So what are the constraints? What are the constraints? Yeah. Hmm?
You can't have, each time slot has to have one section in it.
But there are lots more sections than there are time slots. You can't have.
Multiple sections writing at the same time. So you can't have like there's 100 writing an exam at the same time until you finish the construct.
Why? You have to. There are all sorts of things. Yeah.
Can have multiple sections at the same time and place.
You can't have multiple sections in the same time and place. Maybe.
So each section is a unique time and place.
No, that's where. But that comes from here. That comes from this definition. Each section has a unique time and place. Comes from this.
Because you can put all the sections in one of them. According to that.
Oh, all the sections for the same course in the same room?
Yeah.
Yeah.
But you can't do that. That's our constraint.
Well, you can. In fact, they do. In fact, that's.
No, I mean all the sections that two different subjects in the same room is what they're saying.
Oh, yeah. You can't have two different subjects in the same room. They don't let us do that, in fact. Yeah, thank you. Yeah.
You can't have the same student in 2 exams at once. And you also can't have the same student in 3 exams within a 24-hour time period.
Yeah. Turns out if you try to solve that problem, there's no solution. So here are the actual constraints that they use. We're running out of time. There can't be more than 30 conflicts in a section. There can't be more than 30 students who have 2 exams at the same time for any section. So they let you have up to 30 students who have a conflict at any time. And this happens because if you have a class of 400, 2 classes at 400, then there's essentially no times when you don't have 30 people. Yeah?
Is that number growing as more students?
I don't know the answer to that. In fact, the person who wrote the system will give it to us. You can ask him. For each exam, there are allowable rooms, because there's only certain rooms that some courses can fit in. If you need some particular feature in a room, there's allowable features. Unrelated exams can't share a room because you need to make announcements for one particular course and it's going to disturb the other one. Cross-dis listed courses must have the same exam time. So if you have 2 courses that are the same course, but one's an ECE course and one's a CS course, then sometimes there's the same number for the same course. That has to have the same time slot. And evening courses must have evening exams. So they're the hard constraints that they satisfy. And then there are a lot of preferences. And then there are a lot of soft constraints. They try to minimize. Once you have those hard constraints, there are certain things you can do. And then you try to minimize the number of conflicts, the number of students who actually have 2 exams at the same time. We don't set that to 0. We have to try and minimize it. We try and minimize the number of students with 2+ exams on the same day, students with 3+ exams in 4 consecutive times, students with back-to-back exams, less than 8 time slots between exams, preferred times for each exam and preferred rooms and room capacities, and first-year exams shouldn't be on the last 2 days, and fourth-year exams shouldn't be on the last 2 exams and the spring exams. So there's lots of constraints we try to minimize, as well as these hard constraints. That's a sort of real-world problem that people have. Okay, let's stop there.